Okay, here's question 2 from 8.4, the first worksheet. It asks, does the series -1 to the n minus 1 over 2n plus 1 converge absolutely, conditionally, or not at all? So it's really asking two basic questions. Does it converge, which we would have to answer on its own. Then we would ask the second question, does the absolute value of it converge? Now the reason that I wrote the notation here is to make sure that the absolute value is on the terms, not outside the series. Those are very different things. We've never written the other, I don't intend to write the other, I don't want to make it a confusing point. So, to answer these two questions, we're going to start with the original series. I'm going to use the alternating series test because I see the alternating -1 to the n minus 1. From n equals 1 to infinity, -1 to the n minus 1 over 2n plus 1. We're going to consider b sub n to be the same series if you're calling the series a sub n. B sub n is the same thing without the negative. So 1 over 2n plus 1. To converge according to the alternating series test, we need two things to happen. We need to make sure that the limit as n goes to infinity of b sub n equals 0, and that b sub n is greater than or equal to bn plus 1 for all n's. Okay, so we need to make sure of those two things. So we're going to check them. First, the limit as n goes to infinity of 1 over 2n plus 1, well, that pretty easily goes to 0. The 2n plus 1 increases without bound. So, check mark. We got one thing we wanted. Then we're going to take the generic guy, 1 over 2n plus 1, and we're going to compare it to 1 over the next guy, 2n plus 1 plus 1. So this is a guy, and this is the next guy. That's important because we want this to be true in generality. We don't want to just use a 7 and an 8 and show it's true, because that doesn't mean it's true forever. There are many facts that are true sometimes, but not always. So we need to do it with the variable n so that we can make sure it's true. We're going to simplify the right side. That's 1 over, because this pops up in many ratio tests. Notice that the n plus 1 replaced the n, right? So this is going to be 2n plus 2 plus 1, which is 1 over 2n plus 3. So we're now comparing 1 over 2n plus 1 to 1 over 2n plus 3. If you divide by something bigger, 3 is bigger than 1, you get something smaller. So it did decrease. We want to make sure that the guy is bigger than the next guy. And if that always happens, then it has to be decreasing. So we're decreasing. So our limit's 0, and we're decreasing by the alternating series test. The series from n equals 1 to infinity, -1 to the n minus 1 over 2n plus 1 converges. One of the easiest tests, because the two things we checked are so simple. I talked a lot about them, but they're pretty simple. So, does the absolute value part converge? If so, then it converges absolutely, which you remember is strong, and it means you can rearrange things. If it doesn't converge absolutely, it's an okay series. So, we're going to consider, does the series absolute value -1 to the n minus 1 over 2n plus 1 from n equals 1 to infinity converge or not? But that's the series from n equals 1 to infinity of 1 over 2n plus 1. Yes, this looks like what we just did, but before we had bn is 1 over 2n plus 1, and now we actually have the series of 1 over 2n plus 1. So we have to start fresh with our tests, okay? To use our tests, I would ask divergence test. Well, it doesn't look like it's going to go to anything but 0, so we can't use that. It looks kind of like a p-test. Looks kind of like a 1 over n to a power, so let's check that. Let's compare it to a p-test. So I want to compare 1 over 2n plus 1 to 1 over 2n. If you divide by something bigger, you get something smaller, and 1 over n. Multiplying by 2 makes the 2n bigger. Divide by something bigger, you get something smaller. So the series we're working with is less than 1 over n. And we know that the series 1 over n diverges. I'm okay with hearing by the p-test with p equals 1, or because it's the harmonic series. It has a name for a reason. That's from n equals 1 to infinity. So we are smaller than something that diverges, which doesn't help us. So we've got to try the limit comparison test, which is our fallback. Oops. Let's use the limit comparison test. That says, look at the limit as n goes to infinity of a sub n over b sub n, and I let a sub n be the guy I started with, and b sub n be the guy that failed me. So he has a chance to redeem himself. This is the limit as n goes to infinity of 1 over 2n plus 1 divided by 1 over n, which is the limit as n goes to infinity of n over 2n plus 1. And if we remember lots and lots of different ways we can show, this is just a 1/2, looking at leading coefficients or anything. Since this limit is since 0 is less than the limit, and it's less than infinity, it's a finite number, the series do the same thing by the limit comparison test. So we were comparing 1 over 2n plus 1 to the harmonic series. Since 0 is less than 1/2 is less than infinity, the series 1 over 2n plus 1 from n equals 1 to infinity also diverges. Having a limit between 0 and infinity means they do the same thing. Since we already said that 1 over n diverged, our answer must diverge. So that's it for that one.